Welcome to the Module 6 of the Milton-Madison Bridge Replacement Project. We're pleased to introduce our speaker, Charlie Gannon. Charlie is Project Manager of Walsh Construction. From 80-inch diameter concrete storage silos designed to hold 32,500 tons of coal to the remaining section of the Indianapolis Canal Walk, Charlie has managed a variety of interesting projects. Always seeking greater challenges, Charlie was thrilled to be chosen to manage the Milton-Madison Bridge project. He considers it the cornerstone project of his 37 years in heavy civil construction. Charlie?
On behalf of Walsh Construction, I'd like to thank FIU for the opportunity to present the contractor portion of this presentation. I would also like to thank those that have shown an interest in the project, and hopefully what we've shown today has answered a lot of your questions. Travis and Murray's presentations were very thorough. I've done my best not to overlap what they presented, so I'm not going to talk much about the design aspect, mostly about the actual construction and some of the difficulties we faced and some of the challenges. You know, the slide of this project was the highlight of the contract. Getting there was a challenge in itself. From working the cofferdams, strengthening the old caissons, the lifts, and the slide, it was all a very interesting project. So I'm going to walk you through rather quickly here, kind of a sequence of how the project was built. And if there's some overlap, and I apologize for that, but hopefully we'll see some, at least some new photos. So as we all know, this was the existing bridge built in 1928-29. We've all seen this picture, but I left it there because I'm going to have an updated one at the end here. No way to start a project. We began the project in December of 2010, and turned out that 2011 was the wettest year on record along the Ohio Valley. The project experienced 8 flood events in the first 14 months, and Walsh lost approximately 240 days to high water conditions. Normal pool was right around 420. For the contract, ordinary high water or a flood day was set for 432.2. And this picture right here was our highest water level, which was Easter of 2011 at 456. The project did not have a lot of room to work. In this picture, you can see the causeway that was built to allow access to the river from the Indiana side. But basically, along this line right here and over and back down this line right here was our work area on the Indiana side. We rented a 7-acre field from a local property owner for our laydown and pre-assembly yard on the Kentucky side. And we also built a trestle to allow us to get out to deep water. And the work platform, this portion here, was designed for a 275-ton crane with a max pick of 100 tons. Seen pictures of the cofferdams in the previous presentations. Because of the limited headroom, we could only drive sheets that had a top grade or top elevation of 435. So if the water was coming up and we knew it was going to continue to come up, right around 430 was when we had to take our equipment and fleet it until the floods receded. So we were limited somewhat by the height of the sheeting as well as the flow of the river in our working. Here's a picture of the pouring of a 6-foot concrete seal inside each river cofferdam. And part of the process of work on the caisson, which Travis did a very thorough job of describing, was coring of these holes. So I thought I'd give everybody a chance to look down inside the old caisson. And then here's a picture I think we've seen before of the bars being ready to be grouted. One unique thing about the anchoring of the reinforcing steel in the caisson was we had to prove to the owner the bond strength of the grout that we were using. So we actually had to set up a test. The test was specific to the contract. But what we found as something that was unique was no one in this part of the country had ever tried to pull a bundle of bars. Single bars, yes. So we actually had to reach out and get some specialty wedges built in order to pull a bundle. We also were told by the grout supplier that in order for the grout to have the strength necessary, we would have to roughen the edges of the hole, which did not sound like a cheap proposition. During our testing, we roughened some holes and left some holes slick from the coring, and as it turned out, there was no difference in the bond strength from either a roughened surface or smooth surface. This was mentioned earlier by Travis, the number 7 epoxy-coated resteel shear connectors. There was over 7,000 of them drilled and anchored in the existing piers that were strengthened. Also talked about the reinforcing steel, a couple of pictures of what the steel looked like in application. Our forming system was an FCO forming plate girder system. We poured 20 feet at a time. And each time we would break it apart, clean them, and then jump them up. The way we poured these pier strengthening sections was using concrete pumps on barges, and to feed the pumps, we had 2 barges. Each had 4 4-yard concrete buckets on there, so we could bring out 16 yards at a time and feed the pump trucks via crane and bucket. It works quite well. And you can see the wrappings on this one. Once the concrete got more than 4 feet thick, we were obligated by contract to use mass concrete thermal control measures to monitor the cure of the concrete as it related to heat distribution. So here's a picture of a completed pier with the pedestal steel standing tall above it. The concrete thickness varied in the jacket from 2 foot to 6 foot. This was an all too common occurrence. This was the next section of, in this case, Pier 4A to pour, and the river had other ideas. And the cleanup after these kind of situations were very labor intensive. Travis talked about the temporary ramps. Here's a good cross section of what the ramps look like. To expound a little bit on how these were anchored to the beams, we use a standard carriage bolt and what they call a lug C washer, which is bent in such a manner that you can reach through the timber and grab the flange of the beam below it. They're used for docks mainly, and they held quite well. Just another view. We use 24 and 28-inch pipe piles to support it, and you can see the stringers underneath. Just another view prior to paving that section of it. And portions of the Kentucky temporary ramp was an earthen fill. One of the key elements of our first closure to connect these ramps was getting sections of the old approach spans out of the way. In order to expedite the installation of the remaining section, we actually drove the support piling on the outside, and you can see the piling right here that will accept the cap beams for that section that remains to tie the ramps to the old truss, and hurried our demolition contractor along to remove the deck off this portion. And that you can see him shortly after midnight of the night we closed it, hammering the deck down. And then the next day, about 1 o'clock, we actually had that section fired and dropped. The demolition expert dropped it straight down, it did not hit any of the piling, and that allowed us to go right to work on setting the cap beams. And Travis used this picture previously, but we had to install the cap beams, the stringer beams, timber mats, concrete barrier, and place the asphalt. And we did this, the closure was only 3 days before we could put traffic back on the existing bridge. And here's a picture of the work on the Kentucky side showing the installation of the stringers. There'll be sections coming back this direction to complete this. We finished asphalting in a heavy rain at midnight in order to get it done without being charged a 4th day. It was prom night too, and the people in Kentucky were happy they didn't have to drive over an hour to get the kids back home. This is the temporary pier on the Indiana side in action. It was posted at 15 tons and limited to vehicles of a maximum of 30 feet long. And it was only set to perform for a few months, but ended up being in use for over 13 months. Through a winter, we had to plow it, and it worked fine. We had weekly maintenance where we kept bolts tightened and we checked for any other issues. But the ramp system worked very well. During that time, we began the pre-assembly of the truss. Part of that was lashing big jumbo barges together and setting up what is called a grillage system to support the truss. And it was very important that everything was surveyed in to be exactly to within a 1/4 of an inch and to allow the truss to be properly assembled. The crews did a very good job with this. This is a shot of the first section of span 2 being assembled on the barges. And we fed that operation by some float trailers within the yard. The next members we loaded up and pushed out using a big loader to move the float trailers into place. Just a point along the way of the span 2 being assembled. For the most part, we used aerial lifts setting on the barges for the iron workers to access the connections. It works quite well. You can see the aerial lifts all over this barge. Here's another picture, span 2, almost completely pre-assembled and work progressing. And the painters would also use these to paint the connections while it's still on the barge. Here's a picture of span 2 basically ready to be lifted and the beginning of span 3 being assembled. At the same time, as described in the previous presentations, we were out driving the piling that would support the temporary piers. Pile alignment was important. That's why we did use the lower barge impact frame as a template. The pipe piles were 36-inch diameter, 1-inch wall thick. We drove a D113 diesel hammer. We drove using a D113 diesel hammer, for those who understand diesel hammers, and we had to achieve a minimum of 2,900 kips. At the same time, we were pre-assembling the temporary piers and getting them into position ready to set. This are the workers adjusting the 4 legs for the tower to go ahead and be able to set that as soon as these were ready. Temporary pier construction. This part over here shows a section being set on top. I should note that the lower sections were filled full of sand to help with the stability of the pier. So that was an operation in its own. And then this is what the pier looked like at this stage. At the same time, as soon as the pier strengthening was done, we move a crew in to form and pour what I call the sliding girder pedestals or the tine pedestal. And as Travis mentioned, there's a lot of re-steel there. On average, the 3 had about 24,000 pounds of re-steel just in the pedestal. Here's the crew forming it. It was a very uniquely shaped one, so it took some creative form work to get it ready to pour. And then once completed, you can see some of the V-strips, and there's inserts in here to accept some shear connectors just to tie all this massive concrete to the permanent pier once it was poured. Here's a close-up of the jacking tower atop the temporary piers. You can see it on this side here, set there strictly for the strand jacking of the span. And this is the beam that accepted the sliding girder. You see an opening right here. I like this picture in that you can see the size of the structure compared to the workers here. So here's a picture of the towers in place, both at Piers 3 and Pier 4. At the same time, the pedestal is being formed. A lot of activities had to go on at the same time to make up for lost time from 2011. Here is an installation of the jacking platform bent that Murray talked about. And here is the assembled tying girder assembly, staying on the ground, ready to be lifted, put on a barge, and carried out and installed in place. The position of this was very critical for obvious reasons. And here you can see this being set in as a single piece. Seeing this picture on the last presentation gives you a neat perspective of the opening that the girder would slide in. And this right here and the one below were what we call the blocking beams that allowed that girder to be cantilevered while they were shifting the rigging to slide it on in. Here is the positioning of the jacking platform. It's going to set atop the jacking tower and the jacking bent. And here it is in place and being bolted by the ironworkers here. The next step was to connect the lower barge impact frame to the pier. You can see we've taken out the end of the cofferdam here in order to make that connection. This was very tricky in that these were surveyed in and cored and fastened to the outside of the pier stem while still inside the cofferdam, and then make sure that we made it up correctly with the legs coming out here to the barge impact frame. And for the most part, it worked pretty well. Here are the 350-ton jacks ready to have the strand jacks, the strand installed prior to lifting to the platforms. Here is an in view of one of the strands. This is altogether 5/8 of an inch in diameter here, all 7. And they would be one at a time pulled through the jack, locked into place on the ground. Here's a picture of the wedge assembly. There's part of the lifting itself. You can see the wedges in here that actually would grab a hold of the strands to either pull it or to hang on. And then once the strands were fully installed, they would lift jack and strands up onto the platform. And in this case, this is Pier 3. All 4 jacks would be readied. You can see the control lines all coming up to a central manifold that ran the jacks. Murray talked briefly about these yoke assemblies that were used during the strand lift. These were tricky little things to install. Rigging is one thing, but keeping them in place until you could get them anchored was another. Once span 2 was ready to lift, we began the float in at daybreak. And this is just a series of photos of the truss being positioned ready to lift. We floated in on a Monday. It was an equipment issue. We had to get tugs, and they was available like 4 days before we wanted to lift. So we went ahead and brought it in position, and it sat there until Friday. This was a Monday, and it sat there until Friday before we started the lift. But it was a very slick operation moving this into place. Span 2 weighed about 1,700 tons when it was lifted. This is about halfway up, probably to the point that Murray described where the lower leg had to be brought up to support it. Here is span 2 all the way to the top. And now we bring the sliding girders in. Another shot of how it was brought in and connected to the tines. Here again, you can see the size of all this works based on the size of the workers here. And this operation went very well in the 3 times that we did this. You can see the married up tines and girder being rolled into place using Hillman rollers. And then here it is in place, ready to set the bearing down, and you can see a tie down right here that has the tines secured to the pedestal itself. Same operation for span 3. It weighed 1,900 tons at lift. We started that float out at midnight. We only had 24 hours to have the main channel closed, and so we started the float out slightly after midnight, and by 7:30 that evening we had it up and secure where we could reopen the channel. That was a very successful day for us. Here's a picture of span 1 being erected in place, stick built as we called it, and it's cantilevered out, and you can see workers here working on the connections. And then both spans 1 and 4 used what conventional stick building. These are called floats. The iron workers would build these and they could move them from one location to the other as a work area. And yes, both of them are tied off 2 places. Here's another group of pictures of the workers stick building in operation. Here they're tying a diagonal to a lower cord and they're bringing in the post here and making the connection. That's called hanging out there. Once the truss was assembled, it was time to survey the deck and then put the SIP, stay in place forms, down in order to start running the reinforcing steel. At the same time, we're running an overhang to carry the coping. Here's a shot of the deck with reinforcing steel in place, and you can see the parapet reinforcing over here for the guardrail system and a track for the machine. We poured the 2,400 foot long deck in 3 pours, 800 feet a shot. So we poured the south 800 feet, then the north 800 feet, and then we filled in the middle. We moved the concrete from the end of the bridge out that 800 feet to start with by using a stiff line that would pump the concrete out into what is called a spider. It's a little distributor for the concrete. And so you can see the pipe coming in here. This pivots 360 degrees and it tilts up and down to help move it in a tight area. Very convenient for this kind of pour. So once the deck was poured, the guardrail system installed and stripes put on the bridge, and then we connected the permanent approach to the new truss on its temporary supports with this little transition span. We could open up to traffic. This did not require a closure. And this is what the Kentucky side looked like here. So we have traffic coming up, the new approach going on to span D, which was talked about, onto the truss. Once the traffic was moved off the bridge, it was time to demo the bridge. This is a shot of the first span being dropped using explosive cutting into the main channel. And then Murray has a similar picture. This is the second frame of that sequence. And the point here is how close we are to the existing bridge and how important it was for this to fall straight down, which it did. But also notice the debris flying in the air. That caused a problem later on. Once the portions of the old caps were removed, we could go up and start the new cap work. Here again, we used FCO forming systems to form and pour the cap. There were some one-of-a-kind forms in here for this. Just a picture of the shape of the first part of the pier cap pour. And here is the picture of the truss system on top that was put there to help carry all the embedments that were needed for the slide. We took advantage of the new truss setting there by maintaining some traffic and setting up on the new bridge to pump. This allowed us not to have to use barges like we did for the pier stem strengthening. It worked very, very well. Most of the pours started at night, had to do with the mass thermal concrete control measures that we were in, and just the time it takes to pour 700 or 800 yards this way. And this is a completed section of the pier being ready to accept the slide. I threw this in here. It shows a good shot of span D. I won't spend too much time on the span D slide. Travis did a great job presenting what that was all about, but this is where span D was located. And here's kind of a close-up of what it looked like prior to the slide that day. And this is about halfway across. And then the shot, we can see it in line with the new approach span and where the truss will be in just a few days. Some by the numbers here. Murray touched on this, so we'll move through this fairly quickly. Talked about the dimpled PTFE on polished and greased carbon steel, permanent bearings utilized for sliding, thickness of the slide plate, and the widths. And it was very critical that the slide plate was flat, and the hose slide was guided only at Pier 4. The Bravo laser system actually was VSLs. They were our lifting and sliding experts. That was their system to control the slide in this case to keep it in line. They like to keep things within 3 millimeter as they slid. And then we used the bearing harness system to pull it, and we use the same jacks as we use for the lifting to pull. And here's another picture at Pier 4 of the jack setup. Murray did a good job of describing this. Your jacks, your rollovers, your bumper here already as the truss was coming closer. Another shot of this PTFE, and I will explain on one of the questions that was brought up on the last segment. We added this plate as part of our design to be a permanent plate. So once this was in place, this was welded solid to the masonry plate. So the Teflon at that point had no further use, so there's no worry about wear here. However, the wear here on the bearing itself, stainless against Teflon, would be what would wear over the years. If you need to replace it, then you pull these plates off here and the upper plate and replace it with new, but this became a permanent part of the structure. Here's the crew polishing the slide path. This is Pier 4. You can see the guides on either side to guide the path of the slide. This is Pier 5. You can see just one row on one side. It basically is just holding the plate in place and no guide necessary. This is the bearings at the two end vents. They're sloped because of the design of the bridge, and to keep these from wanting to slide out, they created a nifty little thing called the stuffer, and you can see a screw jack affair right in here that could be adjusted to keep pressure against that bearing as we slid to keep it from wanting to slide out. This became a very interesting little design that was kind of spur of the moment and took a few days to get that fabricated and then installed. This is the lead bearing harness for the two end vents, this Pier 6 as it would be. You can see the strands, and then these tie rods that tie the lead bearing to the trailing bearing, which is this is the very opposite end, and these two little features are called the skates, and it just helped or prevented this portion of the harness from wanting to sag a little bit. And this is Teflon sliding on the grease surface. This is the lead harness of the three main piers. You can see the covering over the strands, protecting them until we got ready to slide. And this is the opposite end of that. You can see the strands coming in and tied off with these anchor blocks. And then you had threaded rods, big tension rods that went to the rear and gathered up the trailing harness. And here's workers connecting the harnesses together with the tension rods. The Bravo system, this is the laser right here, and the target was on the truss itself. Control center, sliding surface. These are our wind brakes. As Murray mentioned, we had to stop the first day because of some wind considerations, and so we spent that evening and then started the next day. And when we got ready to slide, the workers would back this plate off 24 inches, allow the slide to happen, and then we would tighten it back down to prevent the wind from wanting to push it. This is about halfway across on the first day, and then finishing up the next day with just a few feet to go. And shortly, about 7 days after we finished the slide, all of the bearings were installed, all the restraints installed, and we were ready to open up the bridge to unrestricted traffic at that point. But we weren't done. We then had to do the closure pours on the pier caps and remove all the temporary works. So you can see this section here, which was the pour back section. The workers did a very good job of tying that in and making it look like a monolithic pour. Here is one of the last things we did to stabilize the pier design, was to install the balance of the scour rock. The scour rock varied from 12 to 37 inches in diameter and was placed 12 feet thick around the pier out as far as 45 feet, the three river piers. So here's the new Milton-Madison Bridge. Very pretty. We think it looks like what the owner was hoping for. And lessons learned. When you work on the river, come prepared to battle worst case river conditions. We learned the hard way, but cutting your teeth sometimes. Consider demolition methods when old is adjacent to new. I would not advise using explosive cutting charges in this application. I think the proper thing to have done, and maybe even been required by contract, was to force the contractors to actually lower the sections on the barges and float them away for demolition. Avoid shot painting a truss before assembly if at all possible. We had schedule constraints on this job. We didn't have the luxury of having time to paint the bridge once it was fully assembled. So we did choose to shot paint it, and there was a lot of touch-up from the blast, from just the workers banging their tools against it. And so it became a very costly thing for us to have to touch this bridge up. And then consider using stainless steel versus polished steel for slide surfaces. The labor cost to polish this steel, I think, would considerably more than it would to have purchased stainless steel like we used on Span B. So that's my presentation. Any questions?
Okay, thank you, Charlie. You and your co-presenters today have shown this excellent example of the impressive projects that are possible with expert teams such as yours in collaboration with all the stakeholders, and wow, with such amazing benefits to the traveling public. We'll now begin the Q&A session. We have a couple of questions. First, can you describe how the mass concrete thermal control system worked?
We set up a manifold system, and we brought tubing, it was basically irrigation piping, off the manifold system and looped it through The formwork, it was designed by a company, CTL, out of Chicago. So we knew how many pipe or how many of the tubes and at what locations. And we would just run water through those tubes, and it would pick up the heat going through the concrete and discharge it out the other end. And what you're doing with mass concrete thermal control is making sure that the interior temperature of the concrete and the exterior temperature of the concrete is within a certain temperature range to prevent excessive cracking by getting too hot or hydrating too quickly. And so we basically would wrap it up tight to hold the heat in on the outside, but then put pipes through the concrete to carry the heat out of the inside of the concrete. And we just pumped the water right out of the river and just returned it to the river.
Excellent. Okay, thank you. And then looks like we have one last question. Did you encounter problems with pumping the truss deck concrete?
Yeah, I wonder if someone would ask that question or not. Trying to push concrete 800 feet down a 6-inch pipe can be problematic. And we did have some blockage. It was usually early in the pour, but for the most part, it worked pretty well. The concrete we were using had some what we call a water reducer in it, which allows you to make it a little bit wetter. So overall, it went pretty well. But if you can avoid shoving concrete 800 feet through a pipe, I would recommend it.
Okay, well, thank you. We're now at the end of the 6th and last 40-minute module. Thanks again to Charlie Gannon and to all who participated in the 6th module. Charlie, as did the other speakers, welcomes any additional questions and invites you to contact him directly. This completes the Milton-Madison Bridge Replacement Project in-depth web training sponsored by the ABC-UTC. All of us at the ABC-UTC would like to again thank Ann, Kevin, Aaron, Travis, Murray, and Charlie for sharing your expertise with participants. Thanks also to all who participated in the web training. The web training has now ended. Thanks.